Hello everyone, and welcome to today's video. I'll show you how you can laminate carbon electrodes onto a perovskite film using hot isostatic pressing method to fabricate a perovskite solar cell. As you can see here, the carbon electrodes are securely attached to the adhesive side of copper tapes, arranged neatly on the perovskite film. Since the carbon electrodes are non-adhesive, lamination is required through hot isostatic pressing. Here's how it's done. First, I vacuum sealed the prepared perovskite film with pre-arranged carbon electrodes into vacuum sealing bag. Then, I place the bag inside a custom hot isostatic chamber and tighten all chamber bolts to ensure a secure seal. I then introduce silicone oil into the chamber using a manual hydraulic hand pump jack to increase the pressure inside the chamber to roughly 5 to 6 megapascal. This high isostatic pressure environment will compress the carbon electrodes evenly onto the surface of perovskite film, without fracturing the glass substrate. The chamber was then placed on a 100 degrees Celsius hot plate and heated for 10 minutes. Afterward, I depressurize the chamber, and the sample is ready. As you can see, the carbon electrode is now securely bonded to the perovskite film, and no matter how I try to scratch them, they won't delaminate. With this lamination complete, the perovskite solar cell is now ready for efficiency measurements. The device was able to yield a decent efficiency reading of 8.21% and is expected to show more improvement with further optimization of the hot isostatic pressing process. Thanks for watching, and I hope you found this video informative.
Ammonia sensor incorporated with polyvinyl alcohol reinforced Clitoria ternatia anthocyanin for zero power ammonia sensing. Ammonia can be sourced from companies, fertilizer, and from our surrounding itself. Beyond the threshold level, ammonia will injure the human respiratory system, irritate the eyes and skin, and cause death if inhaled over an extended period. This problem can be solved by incorporating commercial sensor. In this study, we will look into a zero-powered sensor for ammonia sensing. This is the fabricated sample. Let's look into the proof of concept, whereby we can see the obvious color change due to the presence of ammonia. This concept is mainly done to show the sensor ability to detect ammonia in our environment. On the other hand, ammonia can also be detected from protein-rich foods such as fish, shrimps, and meat. Humans tend to buy protein-rich products from supermarket without knowing its freshness and durability. By using a food quality monitoring tag, we can actually detect its freshness. With this, we can reduce food wastage and prevent food poisoning. In this study, we will look into food quality monitoring tag that helps consumers to detect the food freshness from observing the color change. This is the fabricated sample. Let's look into the proof of concept. I always go to the supermarket and wonder if the food that I'm buying is actually fresh. It looks good to me by seeing with my naked eyes. Does this shrimp actually stays longer according to the expiry date stated on the packaging? Let's study the freshness of shrimp. This is the result after keeping the shrimp in both room temperature and inside fridge. When it has been kept in room temperature for 6 hours, the color change from the presence of ammonia can be seen with our naked eyes. Thus, it is proven that ammonia can be detected from both environmental and in food.
This video demonstrates the synthesis of tapered fiber vibration sensor using optimization methods. The Structural Health Monitoring, or SHM for short, uses sensing technology to perform localized structural deterioration monitoring. It can be applied in the maintenance of buildings, pipelines, etc. This monitoring method senses and monitors the change of vibration propagating through the structure. The vibration sensor used in this demo is the Loop Integrated Tapered Fiber, or LITF for short. The LITF is a type of inline cascaded Mach-Zehnder interferometer. It consists of two biconical tapered fibers, or BTF for short, and a central loop. It performs vibration sensing by detecting the physical strains induced on the loop by the vibration. The collected vibration signals are analyzed using a model-based signal reconstruction method named the time domain reconstruction model. The model requires the input of the collected vibration signals and the bending response of the BTF. It performs signal reconstruction with the help of a type of swarm intelligence optimization method. This model outputs the reconstructed signals, the estimated frequency in the initial phase of the collected signal. Here is a little demonstration of the optimization process. This is the end of my presentation. Thank you.
This demo is to showcase on the topic Data-Driven Alternating Direction Method of Multipliers, ADMM, with Physics-Informed Neural Networks, PINs, and Sparse Optimization. It will first start off with the demonstration on how neural networks could be adopted to train the dataset, followed by the explanation of the concept for sparse optimization, then finally to demonstrate a simple example of coupled first-order ordinary differential equation using the proposed method, which is ADMM.
What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images.
This is the example of the coding when it is running. It will show us for the case of optimization. Then at the end of the training, it will then show for us for the plotting. As for demonstration purpose, like we can see comparison of our ADMM with the numerical method, it fits well. Losses from the pins also minimized, as well as the losses of sparse also minimized.